Okay, so today we are going to talk about the basic idea of some recent paper that I wrote, which is about trying to write some quantum state describing anti-de Sitter space using a finite spin network. So what we are trying to achieve is we're trying to write down a quantum state on a time slice of the space-time depicted on the left, the cylinder describing anti-de Sitter space, and we want to do it in such a way that we describe this quantum state using a finite number of degrees of freedom. For example, this spin network depicted on the right, we see it has a finite number of edges and a finite number of nodes. So what is the motivation for this research? So first of all, there's some interesting recent work on ADS-CFT and holography in general and its connection with loop quantum gravity. And here the hope is that we can use the non-perturbative quantization techniques that we have developed for the gravitational field in loop quantum gravity and apply them to this correspondence and maybe probe new sectors of the correspondence or simplify some existing computations. Next, there's of course a general interest in having a good description of non-compact spacetimes in loop quantum gravity. There are some proposals for this in the literature, but clearly more work is needed, and the paper here is also one of those works because it gives a proposal of how a non-compact spacetime or an infinitely large spacetime can be described in this context. And then for both of those, it's of course interesting to have a finite number of degrees of freedom describing some infinite space-time, just because if you want to do an explicit computation in the end, then having a finite number of degrees of freedom is of course of great advantage because you truncate the problem to some finite sets of degrees of freedom that you're interested in, and computing with those degrees of freedom might already be enough to kind of get the answer that you are interested in. So what is the issue that we have to deal with here? So let's first take a look at anti-de Sitter space, which is depicted on the left here. So we can basically write this cartoon of anti-de Sitter space where it is this cylinder that you can derive using conformal techniques. And it has a time direction which is going upward. It has a radial direction which is going to the right. It has a bulk which is the interior of the cylinder, and it comes with a boundary. In particular, it's a time-like boundary. Now, in addition, you can draw this time slice into this cylinder depicted here, and well, this is the slice on which this time t is constant. And in particular, we're interested in such a slice because we are having a canonical quantization in loop quantum gravity, and we are working on such a time slice. So the metric for anti-de Sitter space is depicted up here. This capital R is just the inverse of the cosmological constant, and small r runs from 0 to infinity. So the issue that now arises is so what happens if you compute, for example, the proper distance of some curve running from some point radially outward to infinity, for example, this red curve here. So in order to do this, or in order to compute its proper length, you just integrate the square root of GRR up to infinity. What is GRR? Well, we just take it from the metric above, and we look at this integral. Now GRR goes as 1 over r squared as r goes to infinity, as we see. If we take the square root, it goes as 1 over r, and therefore we find that this integral diverges. This means that this distance radially outward is infinite, and therefore also an analogous thing holds for the volume. Also, if you compute the volume of this time slice, it will be infinite, and therefore you will not be able to describe this time slice using a finite number of vertices in the standard construction at least, just because with a finite number of vertices you would get a finite total volume. So what is the idea of how we are going to solve this problem? So what we're going to do is we're going to take anti-de Sitter space depicted again here, and we're going to conformally compactify it. So the idea of conformal compactification goes back to Roger Penrose in the 60s, and it was applied to the context of ADS by Ashtika and Magnon. So the basic idea is that if we have some infinite distance, for example this red line here, and it's infinite with respect to some physical metric g mu nu, then what we're going to do is we're going to conformally rescale the metric in such a way that after the rescaling we get a new metric g twiddle, and with respect to this new metric this length is now a finite distance, and it will just fit into this cylinder. So of course, if you know how conformal compactification works, then you also know that these conformal diagrams, like this cylinder of anti-de Sitter space, are exactly derived by such a conformal compactification. So what we're doing is we're taking, for example, this physical metric g mu, we multiply it by some conformal factor omega squared, and then we get this new metric g twiddle, with respect to which this line now has a finite size. Now, in order for this to work, this omega needs to satisfy that it falls off as 1 over r in anti-de Sitter space as r approaches infinity, which means that as r approaches the boundary. So this is exactly the idea that we're going to employ later, however, in a slightly modified version. So how do we implement this? So we're just starting by the standard canonical formulation of general relativity in terms of the ADM variables. And there our canonical variables are a QAB, the spatial metric, and capital PAB, its conjugate momentum, which encodes the extrinsic curvature of our slice. So now we're going to take a conformal factor omega squared, and we're going to multiply the metric with it, getting a new metric Q twiddle. And we're also taking this P, and we are going to multiply it with omega, however, with the inverse of omega squared, so with omega to the minus 2, obtaining a P twiddle. So then, by such a conformal rescaling, Q twiddle and P twiddle still have their standard canonical brackets because the factors of omega just cancel. So the question is now, what is a good choice for this omega? And you have to be a little careful here, because if you're not careful, then you might run into problems with diffeomorphism invariance later. So a good idea is, for example, just to take a scalar field, which you already have in your theory. So if you consider GR coupled to a scalar field, and you look at the solutions which are asymptotically ADS, for example, black holes, then you find that these scalar fields typically have the right fall-off conditions to serve as such a conformal factor. So they just fall off as 1 over r at infinity, and therefore things work. Now, if we just compute the proper distance again with respect to this twiddled metric, now QRR twiddle, then we find that if we do this integral, we take the square root of this Q twiddle, from the conformal factor we get an additional inverse power of r, therefore the integral is dr times r to the minus 2, and the answer is clearly finite. So what are the results that we have obtained? So first of all, we can now build connection variables from the rescaled variables. That is, we just do the standard canonical transformation or phase-space extension that we do in loop quantum gravity to go from ADM variables to connection variables, but we do not insert the ADM variables, but the rescaled ADM variables. This gives equally well connection variables, which we can use for the quantization process. As a consequence of this, we will find that quanta of geometry are now quanta of rescaled geometry. That is, if we, for example, draw some link of a spin network, and this link intersects some surface over which we have defined, for example, an area type operator from the fluxes, then we find that the quantum number on this link, it will not measure area, but it will measure this rescaled area omega squared times the physical area. And then also we find that we have this spatial boundary at some finite rescaled distance. This means in particular that after some finite number of nodes we will be at the boundary, and at this boundary we have the standard machinery that was developed in the context of a black hole entropy in loop quantum gravity. That is, we can, connection variables that we use, they induce some boundary theory which we can write as a Chern-Simons theory on the boundary. So what are the open questions in this business? So first of all, I have not told you how one can actually construct some, in some sense, good states describing anti-de Sitter space. So we just showed that with this conformal rescaling, we can in principle write down states which are some useful truncation of ADS using some finite number of degrees of freedom. However, I did not say in general how we now on these graphs construct states which really correspond to ADS. So you could now, for example, just take the coherent states that we have in loop quantum gravity, put them on this graph, and then you have kind of a truncation of ADS on such a discretization. However, the question is if such a state is really useful for what you want to do in the end, and that is not so clear for now. The other thing is that the Hamiltonian constraint obtains a boundary term just due to the standard Gibbons-Hawking boundary term, and this we would of course also want to include in the regularization of the Hamiltonian constraint, and this has not been looked at so far. So this is in particular interesting from the point of view of how this boundary Hamiltonian would act on boundary states. Also, there's an open question about what are the appropriate asymptotic symmetries of such a quantum spacetime representing ADS. We of course know what the asymptotic symmetries of ADS are at the classical level. It's just a certain conformal group. However, the interesting question is how is this deformed at the quantum level? So is there maybe some exact notion of this conformal group, or is there some deformation, which is then especially interesting because such a deformation might also be showing up in some CFT dual to this quantum gravity theory on ADS. So thank you very much for your attention today, and stay tuned for more short talks in the future.